so let's move on. So here is a closer view of some various elements. And I want to talk about these peak shapes. Okay, so we can see here carbon 1s. And all of these are elements. So there's no, we don't have any molecular structures right here. So this is carbon solid, solid copper, solid silver, solid gold. Okay. And so all of these have oxidation states of 0. All right. So carbon always shows up around 285. No matter what kind of carbon it is, the carbon 1s always shows up in the vicinity of 285. Okay. And it's one single peak. Because if you recall, carbon is 2s2, 2p2 in its valence shell. I'm going to get a periodic table in front of me here just for backup. And so if you also recall then that 2s2, 2p2, that's going to make a triplet state. But what's important about that triplet state with both of those electrons being spin up or both being spin down, there is no spin orbit splitting is what we are getting into now. Okay? But what about copper? Well, copper, if you recall, its electron configuration should be 4s2, 3d9. But if you recall, what ends up happening with copper is it's 3d10, 4s1, and that is a doublet state. And lo and behold, when you excite the copper, in this case 2p, it doesn't really matter that it's coming from 2p. What's important is that copper is a doublet. And so when you eject core electrons from a doublet state, you could be ejecting either a spin up electron or a spin down electron, right? Pauling tells us both are possible. And so now something really interesting happens. So you get two peaks because we know that copper is a doublet. And so the two peaks makes copper a doublet. We can also see that they're well separated. And this value of 19.8 electron volts, that is the spin orbit coupling constant for copper. So in other words, when that electron is spin up and it gets ionized, it's going to have a different binding energy than if that electron were spin down. And so if you recall, the 2p level is split by those J values. So there's going to be the J equals 3/2 and the J equals 1/2. And so we also recall here that in this diagram, ionization would be up here. So you can see the spin down electron, the J 1/2, requires more energy to be ionized than the J 3/2. And if you look on this scale here, you can see, so we would typically in XPS, we just put the J value next to that. That's how this nomenclature works. So the 2p 3/2 is corresponding to the 2p level electron, but specifically the J 3/2 electron. Okay, and so you can see that J 3/2 is about 93, 900 and maybe 30 electron volt or so, right? But now you can see as we scan across, the 2p 1/2, the spin down electron, definitely has a bigger binding energy, right? And so from the XPS technique, we can calculate now that this spin orbit coupling constant, or in other words, the difference between these energy levels for copper is 19.8 electron volts. And that's a big difference, that 19.8 EV, okay? So now if we look at silver and get a periodic table in front of you, right, you can see that it goes copper, silver, gold. We recall that silver is also a doublet state. It's going to adopt the same type of configuration as copper, but it's going to be a 4d10, 5s1. So silver is also a doublet. And then now here we're looking at the 3d electron level. And so because silver is a doublet, it's going to have spin-orbit splitting. But you can see that that spin-orbit splitting is much less than it is for copper. And that's due to the fact that silver has a lot more electrons. And so because it has a lot more electrons, that difference of being spin up or spin down is less significant. And you can see when we go to gold, right down the line, gold is also a doublet, 5d10, 6s1. And now we're talking about ionization from a core F level. It also exhibits spin-orbit splitting, but not nearly as much as silver and not nearly as much as copper because of the large presence of electrons. And so we also notice now with our J terminology, right? Recall J equals L plus S through L minus S. And so for the 2p level, L was equal to 1. So 1 plus 1/2 gives me 3/2, and 1 minus 1/2 gives me 1/2. But now when we're going to the D level right here, right? Remember L is equal to 2. So that's where we get the 3D 5/2 or the 3D 3/2. And then for the gold, for the F block, right? L is equal to 3. So that's where we get the 7/2 or 5/2. Okay. You also notice the intensity for the upper lying J level is higher. Okay. And that has to do with the number of electrons that are in that level. So what you can see from XPS is it actually shows that there are more electrons existing in that upper spin level. And this is a good diagram of why that exists, okay? So recall, and this is getting into why the spin-orbit splitting is observed, okay? So if you recall, we have an electron, remember our right-hand rule, we have an electron orbiting around our nucleus. And via the right-hand rule, that creates angular momentum spinning in the up direction, okay? So not only is this electron revolving around the nucleus, but it is also rotating, right? It's spinning as it's revolving. And so when that happens, this high J value, okay? So for example, the J equals 3/2, 5/2, or 7/2. You can see that the electron's intrinsic angular momentum is aligned with its orbital angular momentum, okay? Whereas the low J value, they are unaligned, right? They're anti-parallel. And so that's actually why the low J value has a lower energy and consequently a larger binding energy to remove it, okay? So the binding energy of low J is higher than the high J value, and because of the way those angular momentums are anti-parallel, that makes that electron stuck to the core a little bit, it's bound a little bit more tight, okay? So the magnitude of the spin-orbit splitting increases with nuclear charge. So I have to think about this. Did I describe that correctly in the past? So magnitude of spin-orbit splitting increases with nuclear charge. Oh, and then, yes, so I'm going to go back and re-explain the copper, silver, gold. I'm sorry. So magnitude of spin-orbit splitting decreases with distance from the nucleus. So there's two competing effects going on here, right? Where technically the larger the charge is, the more this effect is going to be displayed, okay? So the larger that charge is, the tighter that electron can be bound. And thus, when you flip it spin up or spin down, the spin-orbit splitting effect is really amplified. However, as we get electrons further and further away from the nucleus, that spin-orbit splitting is less important. So if I go back here, let me explain this again. So if we were looking at all, let's say 2p levels from copper, silver, and gold, then we would see those spin-orbit splittings get bigger as we get on copper, silver, gold, okay? However, we're not looking at all 2p levels, right? It's 2p, 3d, and then 4f. So this effect here of seeing decreased spin orbit splitting in these examples is related to the fact that we're getting further away from the nucleus as we look at a 2p or a 3d or a 4f electron level, okay? All the same, what's important about this spin orbit splitting constant is it is a constant, and it can be used as a diagnostic tool to identify what you have in your sample. So suppose you're analyzing a sample and you don't know what its composition is, right? So when you get doublet peaks like this in this orientation, that will tell you, okay, I'm looking at a doublet state. And then when you calculate from the peak to peak, so that's all the spin orbit coupling constant is just the difference between the peak to peak. So for example, if we saw that it was exactly 19.8, we could definitely say we have copper in our sample. Or if we saw the spin orbit coupling constant of 3.65 with two peaks shaped like this, we could definitely say that it's gold. So that spin orbit coupling constant is a diagnostic characteristic of various elements. Okay. So I know I've been talking quite